Hi there everyone. I'm going to give a brief invitation to our new preprint called the Renormalization of Wilson loop observables via proper flux quantization and cohomotopy. So this follows a talk that I've given last week in Observables at a mini workshop on renormalization and randomness. And we took the occasion to turn this topic into a little write-up. It's to a large part a review of results that we have published previously in the last months and years. But it also has some new components. But I'm not going to go through the article here. I just want to give you a brief introduction of the basic idea and go through the figures maybe of the introduction of the article. So that's the preprint here that we posted just today, which you can find online. But let's look at the actual article and see what is it about. So since this was a workshop on renormalization, and since I don't usually work in renormalization as such, but kind of on its opposite, namely the construction, the eventual construction of complete non-perturbative theories, I took the occasion somewhat theoretically in this workshop to present a bird's eye view on why not to renormalize, if you wish, or bird's eye view on what it is actually that renormalization is trying to get us at, and asking the question whether we can get there in a better way. So in this diagram here, this figure 1, I'm sketching the usual situation as it exists in fundamental physics and theoretical physics these days. So people like to behave, textbooks like to speak as if a Lagrangian density, so Lagrangian like F wedge star F, as you know from Yang-Mills theory or all these other expressions, as if such a Lagrangian density actually defines a quantum field theory, as if it actually defines quantum observables. Now, it's a public secret that this doesn't actually work. If you start with a Lagrangian density and you're actually serious about it, you go beyond the classical theory and actually work out the quantum field theory, you have to go through a long process of incremental fixes, actually, of incremental repairs to the initially ill-defined theory. And historically, these fixes were all also discovered incrementally. So that's why they have these names, as if reflecting the exasperation at the fact that somehow things don't quite work yet. So there's an anomaly which needs to be cancelled. When that is done, the theory is still not normal. It needs to be renormalized. And when that is done, that's actually the worst part even. Nobody speaks about this. You have to resum, which is really a dark art. So the upshot is just that if you start with a Lagrangian density, we compare it in the article to the forktail of the stone soup. Then we're saying, well, starting with the Lagrangian density is just like having a stone for the stone soup. Remember how that folktale goes? It goes like a poor guy arrives at some village, he's hungry. The villagers are rich but stingy, don't want to give any food. So here's this idea, he says, okay, I claim I can make the most fantastic soup out of a stone alone. So he starts putting a pot, boiling water on the fire, puts a stone in it. And that triggers the curiosity of the villagers. So they all come and he claims he's going to make the best soup in the world from just cooking the stone. Of course, the villagers are incredulous, but excited about looking at it. So then after a while, the guy says, you know what, even though this is going to be the greatest soup you've ever seen in your life, of course, to give it the extra edge, if we just had some potatoes mixed into it, that would actually be great. And the villagers say, sure, okay, we can do that. We have some potatoes. So they run off and bring potatoes. And the next he says, this is going to be real great now, but to just give it the last touch, if we just add a little meat to the pot, that will really do great for the final stone soup. And so the villagers go and fetch meat. And now you can see how it continues. So eventually the villagers provide all the ingredients incrementally that it actually takes to make a soup. The stone had little to do with it in the end. They have a soup in the end, and it's called a stone soup. But all the ingredients were added after the stone was added. The stone did nothing but trigger the process in some funny way. And so we're claiming, somewhat tongue-in-cheek of course, that this is the situation with Lagrangians in usual field theory. And while this is well known, it's rarely really discussed. Some people speak about complete quantum theories and UV completion, but this has never been made precise in any sense. There's no standard knowledge of what it would actually mean to have a complete theory and a complete quantum theory. Of course, there's claims that maybe string theory achieves some of that completion, or maybe M theory will achieve more of it if we only knew how it was formulated. In any case, there's this tacit hope that, of course, if you could concisely define a complete quantum theory from the get-go, right away, then the quantum observables should be implications. They should be derivable without further choices in incremental fixes. All right, so that's the story, and now let's see what we can do about this. Let's scroll on to what do we have next here. So next I want to highlight at least one way out of possibly many in which it is already clear at the classical level, already, right looking at it, it's clear that Lagrangian densities cannot in general actually encode the full content, the complete content of a gauge field theory or a higher gauge field theory. And the reason is simple, that Lagrangian densities are always local expressions. They are, at least if we're talking about gauge field theories here, as I will be. So the Lagrangian density depends on gauge potentials, usually A, where I mean them here in generality. These could be higher form fields for higher gauge theories. In fact, they could be lower, one form fields and still in higher gauge theory. This is actually the example of 5D Maxwell-Young-Mills theory that we're gonna discuss, where a priori it looks like a one-form gauge theory, a usual one, but actually it has a flux quantization in higher cohomology, which is an exotic, extraordinary one that is not usually discussed. In any case, the Lagrangian densities, like A wedge dA of Chern-Simons theory, depend on this gauge potential. But the gauge potential is just locally defined in general. It's just defined on patches, on charts of your manifold, whereas the full field content, the full gauge field, contains much more data than just the gauge potentials. So if we do choose denoted Y here, an open cover, say, of space-time by charts, then the gauge potential is just the datum on these charts. And next there's actually, in the full definition of the gauge field, after it has been flux quantized, as one says, after it has been promoted to a globally defined structure, namely a cocycle in some differential cohomology theory, has further data on double intersections of these patches, and then further data on triple intersection, and so forth, as indicated in these diagrams. So this process, in principle, goes on to infinity. Of course, in any given situation, it will actually truncate, either because your flux quantization law is truncated in degree, or simply because the manifold that you evaluate on is of course of some finite fixed dimension, which means that these high intersections become cohomologically irrelevant at some point. In any case, so this indicates that there's lots of additional data in a gauge field, in a globally defined gauge field, than is even reflected in the Lagrangian density. And so it's no wonder from this perspective, at least for such gauge and high gauge theories, that if you just write down a Lagrangian, you have no chance to describe a full theory, because the Lagrangian doesn't even reflect the full field content. So this is where we come in. We say, okay, this is our angle and has been in the last years. So we don't know if this is the only thing that really matters for writing down complete quantum gauge field theories, but it turns out it's actually at least a very major step. So we have thought about what it actually means to properly flux quantize high gauge theory, and hence to complete it. And so the logic of this article here, of this talk I gave in Oberwolfach, is the following, shown in this figure 3 here. So on the top line we see the general logic there we follow, and in the bottom part, or bottom 2/3, we see the realization in this particular talk to a fairly modest, I don't want to say toy example, because it has quite serious applications actually to current experimental physics, but it's a modest example of a quantum field theory, namely related to, in the end, to observables just in three-dimensional, even abelian Chern-Simons theory. So as far as field theories goes, this is one of the best understood, you would hope, and yet there are what I would call gaps in the discussion even of basic observables, even of abelian Chern-Simons theory, where the usual renormalization choices, the usual steps to fix the original Lagrangian are quite ad hoc, and actually not universally agreed on either, mainly based on tradition. Anyway, so here's the outline of the logic. So the general approach to completing a theory, high gauge theory that we're following here, starts just with the equations of motion, just the classical equations of motion for the flux densities. And from that, it turns out, one can read off, so from the Gauss laws, the higher Gauss laws of the flux densities, one can read off, by a process involving rational homotopy theory and some other tools of higher topos theory actually, one can read off what the admissible proper flux quantization laws are. And by proper I mean that we do a bit more than is usually usually done in the literature. People are familiar with what is now called ordinary or Dirac charge quantization, even in higher degrees, where you say, okay, let's suppose if we have a closed form, closed flux density, that it is the curvature of some line bundle, complex line bundle, or maybe a bundled gerb, or maybe a higher gerb, and then we call that the flux quantization. But the catch is that in higher gauge theories, certainly in the higher gauge sectors of higher supergravity theories, the flux densities are not actually closed in general. Well, the example of 5D Maxwell-Chern-Simons theory that this article explains at some point, I'm not showing it currently on the screen, has the famous relation, has a two form that is closed, but in addition it's Hochstuhl, a three form, which is not actually closed. It's Gauss law says its differential is the wedge square of the two form. So this nonlinear relation between the flux densities is not and never reflected in the ordinary flux quantization. Going back to Dirac, that you find discussed in textbooks and in research articles these days. So our point is that there's a proper flux quantization that actually does reflect these nonlinearities and the Gauss laws, and that is important for capturing the full solitonic field content of these higher gauge theories, because if the flux law, the quantization law, doesn't even reflect the equations of motion satisfied by the flux densities, it can never reflect the solitons, the solitonic solutions. And there are integral lifts, they're charged lifts to just the ordinary Maxwell kind of equations of motion. Anyway, so we choose this proper flux quantization, which maybe I'll explain here or maybe not. Anyway, so there's some step there that forms a completed theory that is certainly completed in some sense. So I'm not claiming that is the last word on it, but as I said before, it looks like it's at least a major step in what it actually should mean to complete high gauge field theory. So that is the choice we still have to make. And we have to make a choice at some point, because you have to choose your physical theory, right? We have to say what it is we want to be discussing. So there is a choice here in just stating which complete theory we want to be talking about, and we get this by saying, first of all, well, what are its equations of motion and what is the corresponding proper flux quantization law. But once that choice is made, so that's the point now, then everything else should be implied. And a key result that is reviewed in this article and that we've proven before, a provable result is that after you've topologically completed your field content by a proper flux quantization law, it turns out that the phase space stack of the theory, the higher stack that plays the role of the higher gauge phase space, is already well defined, and that's the key point, and its topological shape is thereby completely defined, it turns out, completely characterized by the flux quantization law you've chosen. So the topological shape, sometimes called the homotopy type or the topological realization, that is math jargon for just the topological part of the phase space. It is that which topological quantum observables actually observe. So a general observable, once you have a phase space of a theory, a general observable is a suitably well-behaved function on the phase space, which to each on-shell field configuration, field solution, assigns the value of the given observable, of the thing you observe in that state. And if we just ask for the topological quantum observables, then that means we're looking just at the homology, just sort of as the topologically invariant functions, just the functions that are locally constant, that just depend on the connective components of our phase space. And that turns out to be entirely fixed once you fix your flux quantization law. So that means, from that point on, you can derive the topological quantum observables. The formulas are given in this article, I'm not showing them now. But this is the general idea. After proper flux quantization, at least the topological sector of the theory, of the quantum theory, of the complete quantum theory, so the renormalized, blah, 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 the fully defined quantum observables are defined and are derivable. There's formulas for this, which may be hard to evaluate in some examples. They're easy to evaluate, or let's say, it has been possible to evaluate them in these modest examples that I'm presenting here. But in any case, it's a well-defined mathematical formula with a guaranteed solution which you can just work out, or which you can ask your expert colleagues to work out if you don't know the algebraic topology that is necessary. All right, so that is the general scheme, and those of us who've been following what we've been doing know that we've been originally motivated by applying this step to the completion of 11-dimensional supergravity, right? So there's this folklore that some completion of 11-dimensional supergravity should be the infamous M theory, kind of the ultimate non-perturbative, completed quantum gauge theory of everything. But even though everybody says this, that M theory is supposed to be some completion of 11-dimensional supergravity, there's essentially no statement, maybe except for some matrix model discussions, there's simply no statement for what it would even mean to complete such a theory. What do we even do? Like, how do we even know what we are looking for? What is the form of the final result of such a completion? And so this general theory we developed was really meant to answer that question, motivated by the case of 11-dimensional supergravity, for which we famously proposed and checked proper flux quantization law, namely four-cohomotopy. And what I'm presenting here is kind of a little sibling of that discussion, where instead of flux quantizing the high gauge sector of 11-dimensional supergravity, we look at flux quantizing the high gauge sector of 5-dimensional supergravity, which is famously known to be, as I just said, a little sibling of the 11-dimensional case. It has a lot of similarities, structural similarities with the 11-dimensional case, so it's a good test bed for M theoretic and related discussions. Anyway, so that's the story here of this example that is being worked out and presented in this article. We start with what's called 5-dimensional Maxwell-Simons theory, and what we're really interested in. And so, as you can see, there's a paragraph, a little interlude on a simple argument, simple observation about how there's a constrained dimensional reduction of 5D Maxwell-Simons theory down to 3D Simons, because we want to be the main result is, the main claim is that we obtain the standard story of Wilson loop observables in 3D Simons theory from this 5D Maxwell-Simons perspective. So I should say at this point is that the reason why we don't apply this flux quantization step directly to 3D Simons theory is that the way we understand it currently, the flux quantization, proper flux quantization, it applies to Maxwell type high gauge theories. So those of the form of the high gauge sectors of high dimensional supergravity theories. Essentially, a bunch of flux densities, each of whose differentials is some polynomials in the others, and some self-duality relations, saying which of those are Hodge duals of which other ones. And Chern-Simons theory is not of this form. Its equations of motion just say that the flux density has to vanish, F2 equals 0, and that is not of the form that we know to directly apply a flux quantization, proper flux quantization to. So what we instead do is we say, well, since we're after completing the theory anyways, anything can happen, and so we instead complete a mother theory, 5D Maxwell-Simons theory, which is classically known, by classical argument, classically known to constraint reduce to 3D Simons. Since we're after completing 3D Simons anyways, we can just as well complete something that is a bit richer, but contains it. So this is why we're looking at 5D Maxwell-Simons theory. And then it turns out, this is this middle arrow here, minimal choice. There is, in a precise sense, a minimal choice of a proper flux quantization law. Minimal in the sense of these flux quantization laws are classified by classifying spaces, topological spaces. And they should be, and if you think of them as being CW complexes, so equipped with what's called a cell decomposition, then this is actually the smallest one. It contains a single cell, namely the two-sphere. The classifying space just is the two-sphere. That turns out to the two-sphere, the rational model of the two-sphere, that's how this works, turns out to exactly know, in the code, the equations of motion, the duality symmetric equations of motion of 5-dimensional Maxwell-Simons theory. And that is the condition for a flux quantization law to be applicable, to be admissible. It needs to be classified by a classifying space whose what's called the real rational L-infinity, Whitehead L-infinity algebra is the whatever. Now I'm getting a bit ahead of myself. Is the L-infinity algebra that controls the Bianchi identities of the flux densities. Anyway, so two-cohomotopy, what's called two-cohomotopy, the generalized non-abelian, or let's say extraordinary non-abelian cohomology theory whose classifying space is the two-sphere, hence whose gauge gauge infinity group is the loop infinity group of the two-sphere. That is an admissible flux quantization law for 5D Maxwell-Simons. So this is the choice we make. As I said before, some choice has to be made at some point. It's not that we can get away without making any choices, because we do need to say which physics we want to be looking at. So this is the choice. After we've made this minimal choice, we have we have a globally completed theory in the sense that we have a phase space stack, which describes whose points are the actual on-shell field configurations, including their full topological sectors. So it's at this point a classical looking thing, but of course the phase space goes a long way to the quantization, right? If you don't think of the path integral, but think of properly defined quantization methods like geometric quantization, it's all about the phase space. You start with the phase space, and then just add a little bit of extra data. In the case of geometric quantization, the pre-quantum line bundle, and that defines the quantum theory. So it's essentially defined by the phase space, and something very similar is going on here. We just have this completed phase space, and so we don't just expect, but well, we expect that generally this should maybe define the full quantum theory, but we haven't shown this beyond the topological sector. But it's a theorem that the topological quantum observers, they do follow, as I claimed in the previous arrow here. So now we in this article, in this talk, we go through this derivation, and it turns out in this particular case of flux quantization in 2 cohomotopy, the key theorems that allow you to actually compute the topological quantum observables from flux quantization in 2 cohomotopy are ancient theorems in differential topology that go back to Pontryagin, and that go back to the roots of what is now most famous as the Pontryagin-Thom theorem, even though the non-abelian unstable sector that we're concerned with is actually exactly the sector that Thom is not involved with. So what is now called Pontryagin-Thom theorem or isomorphism or whatever concerns abelian cohomology theories, which are exactly the ones that we don't need here, or that are not sufficient for our application here. We need to go beyond abelian theories, beyond what is classified by spectra, which are kind of abelian spaces, to general classifying spaces. Anyway, so claim is there's something called the Pontryagin theorem, and there's refinements of this due to Siegel famously, and more recently, in the last years, by Okuyama, who put in sort of a last brick in a building that was initially founded by Pontryagin here, and which gave us so when we found that in the literature, and then we saw that this observation or result by Okuyama is the last little ingredient that we need and actually to complete this proof. So then it turns out that the quantum after you do this dimensional reduction now with a completed theory, it turns out that the properly renormalized Wilson loop observables of Chern-Simons theory drop out. So this is really interesting in itself, because as we recall in this section 2 here in this review, the standard definition really of the Wilson loop observables in abelian Chern-Simons theory, even though you would think this is the simplest non-trivial quantum field theory ever studied, about which everything is known. But if you actually go through how the Wilson loop observables are defined, you notice that one starts with the usual mumbo jumbo of writes the Lagrangians, says path integral here, but nothing actually works. All expressions one gets are ill-defined. This is maybe underappreciated, but even those authors who do manage to, as you can for abelian Chern-Simons theory, to find a path integral measure, then the Wilson loop observables is still not a measurable function. So even that doesn't help. And then you still need to mess with your expression. So there's something that has to fall from the sky, that has to be made up just ad hocly, and there are different choices even. Polyakov, who was the original person to look into this, made a different choice than the one that is now accepted, which is the one from section 2.1 in Witten's Jones polynomial article, where Witten says it is clear that, and then states what is now the generally accepted renormalization choice. But it's clear, in some hand-wavy way, in that it looks good and correct, and I think it is correct. But it is not. There's no way to derive this clear statement. It's just a proposal. So the standard Wilson loop observables of Chern-Simons theory involve this renormalization choice, where you declare that even though we thought we started by thinking that our Wilson loops are really just oriented links. No, in order to do some kind of point-splitting renormalization, we actually have to equip these links with extra data, with what's called a framing. So you change what you thought was the actual data defining your observables, and then you still need to fiddle with the expression for the Wilson loop to finally get a well-defined expression, which is of course now famous and well-known, but I'm just saying it's ad hoc, a well-defined expression for the expectation value of the Wilson loop observable. So this all comes out, and the reason from this completion process that I'm describing, and the technical reason is that, if you've ever heard about the Pontryagin theorem, it says that the n cohomotopy of a manifold, so the homotopy class of maps to an n sphere, know about or are in bijection to the cobordism classes of normally framed sub-manifolds of codimension n. So this is it's a fundamental effect of algebraic differential topology, that framing comes in when you talk about what we now call flux quantization in cohomotopy. That, via some theorems, is what encodes framing in some sense. And then one has to still to do a bit of work, because the framing, the way you see it in the Pointryagin theorem, is not exactly the framing of Wilson loops. So one has to work harder. There's a refinement, if you will, or another guise of or another version of the Pointryagin theorem by Siegel, or another, how should one say? It's another statement about the general idea of classifying mapping spaces into spheres, which Siegel's results relates Pointryagin theorem to configuration spaces of points. And if you know that Wilson loops, as you apply a Schoen-Simons theory, for instance, to the discussion of fractional quantum Hall systems, to actual physical systems that exist in the laboratory, then in these systems you see anions, which are described by braid group representations, and these braid groups are the fundamental groups of these configuration spaces of points that really appear in Siegel's theorem here. So that's the story by which one derives that the topological quantum observables in completed 5D Maxwell Schoen-Simons theory after this dimensional reduction really are exactly the framed Wilson loops, and have the correct, or let's say the expectation value by the width of the exponentiated width of these framed links. So this is the main result that I was presenting in this talk, that I wanted to present. I ran a bit out of time, one has to say, as one can easily see from the rambling I'm doing now. Anyway, so this framing, which and the corresponding width regularization of the Wilson loop observer, which is usually defined by hand and in an ad hoc way, just follows here. But I want to emphasize that something even stronger happens. Not just is the renormalization done by the complete theory for us, but something that is easily missed also happens here, namely the fact that the theory tells us that the Wilson loop observables are the observables in the first place. Namely, from this general setup here of completed quantum field theories by flux quantization, we get a formula for the topological quantum observables. There's just a formula for what is the algebra of topological quantum observables, period. And that is the full thing. So you don't get to choose like, oh, I want my observables to be parametrized by links, or I want, such and such. No, there's just, you derive a general formula for the algebra of topological quantum observables. And the maybe a more remarkable effect even, or yet more remarkable effect, is that this general formalism says that Wilson loops are the topological quantum observables. Now, of course, this will not sound surprising, because this is tacitly the standard assumption in the folklore. That's what everybody thinks should be the observables. But how do you go about actually proving this? Usually in the textbooks, people say something like, "Oh, what is a gauge invariant expression that we can form from a one-form connection? Well, we can integrate it over a loop," and then it's so it's kind of a plausibility argument that is usually presented and nothing more. But there's no rigorous proof, or even any proof, that there might not be other quantum observables usefully used for things like Schoen-Simons theory. So this comes out here too. So this is our result, and in this article we go through how this works. And I just want to, before I think maybe I don't go through any details here, any technical details in this video recording, but I just want to amplify that something really neat is going on furthermore, in that after all this general abstract discussion where we talk about fundamental field theories and things that, like M theory, that seem detached from, unfortunately, right, even though it shouldn't, that seem detached from the real world, it turns out that after completing our Schoen-Simons theory, we actually make contact to we find theory that is actually relevant for ongoing experimental physics right now. So, namely, Schoen-Simons theory is widely conjectured or argued to be. There's gaps in that argument, I find, which we discuss in our articles, but it's widely expected to be what's called the effective, meaning infrared effective field theory for what's called fractional quantum Hall systems. So these are systems of effectively two-dimensional electron gases. So you cleverly construct some semiconductors such that electrons get confined to essentially a two-dimensional surface inside them, and then you put a really strong magnetic field perpendicularly through that surface, and you fine-tune the magnetic field strength such that there is exactly so you need a really large magnetic field for this, that there is exactly one electron per some fixed integer number, natural number of flux quanta, right? So by ordinary Dirac flux quantization, the magnetic field itself has indivisible units of flux. So it's some number of flux quanta, and the left part of this little cartoon here is meant to indicate these flux quanta as little flux densities, so as these little blobs, which you should think of as being the concentration of flux lines, which I'm not showing here. Yeah, right. And so the fractal quantum Hall system happens when there's this exact what's called the fractional filling of the Lagrangian levels. Whatever that means, it means that there is, as shown here, there's one electron per number k of flux quanta. In general, it can be slightly more general. It can be a rational fraction here, but let's just say k. And then it turns out, and this is an experimental fact, it's actually not very well understood on microscopic grounds, but it's just an experimental fact that has been observed over and over again. So it's really completely securely established for decades now that, the general fractional quantum Hall figures for decades, that if you now just tune up the magnetic field just a tiny bit to add a handful of further flux quanta on top of this exact fractional filling fraction, then these surplus flux quanta, they will behave like anyons. This is illustrated on the right. So what does it mean? It means that the entire system, this entire system of the strongly interacting electron gas, consisting of a huge number of electrons that are strongly coupled and somehow influenced by this magnetic field and form some funny state of matter. It's now called a topologically ordered state, which is really not well understood microscopically. But anyway, it turns out that if you braid the world lines of these surplus flux quanta, pair of surplus such flux quanta around each other, the whole system picks up its quantum state, psi, picks up a phase, which is, as you can see here, e to the pi over k, where k is that filling fraction. So this is what it means for particles, or let's say solitons, one should maybe say, for solitonic things, so localized distributions of field strength. To be anyonic means that the whole system picks up a fixed braining phase or even a fixed unitary operator on its quantum state as for each braiding of these world lines around each other. And this is what is commonly expected to be described by Chern-Simons theory. So Chern-Simons theory, rather amazingly, these days is actually experimentally realized. And these braiding phases have actually been measured just in the last 4 or 5 years by a number of groups independently in a number of materials. And that matters a lot in this field because there are, if you've ever followed the current discussion about topological quantum materials, there are claims by certain companies that anyons have been realized in the laboratory, and these claims have never been confirmed by other groups, and remain somewhat dubious. But this is for other systems. But in these fractional quantum Hall systems, that's what I'm trying to highlight. We know for sure, as sure as it gets, that they actually contain these anyons, and they're described by Wilson lines. And these quantum Wilson loop observables that we discussed, they are exactly the things that tell you that such a phase factor as shown here should appear whenever there's a crossing in this link that is the Wilson loop. So it's in this way that in understanding the Wilson loop observables in quantum Chern-Simons theory, we're actually talking about a hands-on system that exists in the laboratory, that exists in current physics. And what is more, even though this braiding phase is now clear and understood, there are aspects of these fractional quantum Hall anyons that are not fully understood yet. So there's quite a bit of room actually for theory to provide more information to the experimentalists of how and where to look for anyons in these systems. For instance, it's an open question. So these anyons that we're seeing here, as I just said, they're solitons. So you can't easily grab as an experimentalist any one of these anyons here and move them around and about in a completely controlled way. But that is exactly what you actually envision you should do if you wanted to use these anyons as hardware for what's called topological quantum gates. So for stabilized, decoherence, robust operations that might be used for large-scale quantum computers that everybody is looking for. So even though, right, that's what I'm trying to say, even though this Wilson loops thing does refer to something that is well seen in an experiment, is exciting. There are more exciting things that one can ask if they do happen in these fractional quantum Hall systems, and current theory does not actually answer that question. For instance, the standard use of effective Chern-Simons theory distributes these Wilson loops, and has a bit of trouble seeing, or there's no discussion, let's put it this way, about if there could be, for instance, defect anions with non-abelian braiding statistics in the system. Anyway, I don't want to get into the details. I've already spoken too much about this now. I just wanted to say that once we have this complete theory, there's actually a handful of further predictions it actually makes about what happens in fractional quantum Hall systems. So once you have the completed theory, it's not just that you've retrodicted what people had already assumed, like the proper renormalization of Wilson loops, but you actually learn more about the physics. There's the completed theory makes new predictions and tells you more about the physical system. Of course, that doesn't mean that it's necessarily the correct theory in physics, right? It still needs to be experimentally checked. If the flux quantization in 2 homotopy turns out not to be the correct flux quantization to use in this situation after all, for some purpose, say for this purpose of describing fractional quantum Hall systems, well, you can still choose a different flux quantization law. So that's just the usual story in physics, that of course you have to choose your model and fiddle with your model until you think you've found the one that is actually given to you by nature. Now, all I'm saying here, just to recall, is that in specifying the model, we can go further than has been tradition to do so. Usually specifying the model means write down a Lagrangian density and then incrementally fix it in a long and largely ad hoc process. Add more and more information. And what I'm saying here is that there is a way, at least for topological field theories, to fix the model right at the beginning, to complete it right at the beginning, and have everything else be mathematical implications. And I think I'll stop here. So you can find this article online. So there's a archived version. Of course, as it always goes, just after posting we found more typos. So there's a version 2 now here in the PDF, which I recommend you look at. We also have a 1-page abstract here, extended abstract, which will appear in the Oberwolfach reports, which essentially just says what I just said in a long-winded way in this video here. So it's really brief, as it goes with abstracts. Anyway, you can find more information here, and you can also find links here to the articles that are being used, our previous results that are being used in these discussions. So maybe the link doesn't work right now, it doesn't work. Anyways, I'll stop here. This was already too long. Thanks for your attention. See you later.